In mathematics, monotonicity refers to the property of functions to maintain a direction. Monotonic function can always be increasing or decreasing, but it won't change direction. More formally, when mapping an ordered set x with a function f, if any member of x, x1, is less than any other member x2, then either f of x1 is less than or equal to f of x2 for non-decreasing functions, or greater than or equal to f of x2 for non-increasing functions. For example, consider the function f of x equals 2 times x. If we take any x1, like 1, any x2 larger than it, like 5, is going to be mapped by the function to a value at least as big as x1 is. That's how we know that f of x is monotonic. If f of x were x squared, then f of 1 is 1 and f of 5 is 25. But f of negative 5 is also 25. Negative 5 is less than 1 and f of negative 5 is greater than f of 1. But 1 is less than 5 and f of 1 is less than f of 5. This function is not monotonic. Linguists have noticed monotonic patterns in various aspects of languages. The values in language usually aren't numbers, so we can't just look at a graph or take a derivative to observe them, but they follow a similar pattern of directionality. Adjectives typically come in 3 forms based on how they compare things with other things, and we call these degrees of comparison. They are positive, like big, comparative, bigger, which compares 2 things, and superlative, which compares against everything, biggest. These forms of big have the same morphological root, big. But not all adjectives follow this pattern. For example, the positive adjective good has comparative and superlative forms better and best. This phenomenon of a word changing to a completely unrelated form when inflecting is called suppletion. The mapping from these degrees to the inflections can be treated as a function. We can arrange the degrees of comparison in a sequence of increasing number of entities compared. The inflected forms can be represented with a letter based on the morphological root. Whatever the first one is will be called A. When going down the inflections, if the root is the same as the previous one, we'll call it by the same letter. If it's different from all of them, we'll go up to the next letter. For example, if we look at big, bigger, and biggest, all of them have the same stem, big. So this sequence can be simply represented as A, A. If we look at good, better, and best, the sequence will be different. The first word will always be A. Better has a different root, so that will be called B. Best has the same root, so it's also B. This sequence is A, B, B. As the degrees of comparison increase, the values of the inflected forms stay the same or also increase. This means that the function is monotonic. Languages besides English have other patterns for their adjectives. Latin, for example, has bonus, melior, optimus, which would follow the ABC pattern as all of the roots are different. But what people don't find are inflections of the pattern A, B, A. That is something like good, better, goodest. This pattern is known as the ABA constraint, and this no ABA pattern goes beyond adjectives. It also applies to other patterns like person and case. For example, just looking at the person for plural pronouns, English and German have different forms. That's the ABC pattern, which is most common across languages. Some languages like ABA and Nez Perce have the same form for multiple inflections, which is called syncretism. But while there are AAB and ABB patterns, there's still a lack of ABA. That is, there's no syncretism between the first and third person to the exclusion of the second person. Monotonicity can appear not just in the forms of words, but in their meanings. Quantifiers are phrases that express amounts or quantities. Quantifiers can take 2 sets of things and relate them to each other. For example, the sentence all cats sit quietly involves the set of cats and the set of things that sit quietly. If the sentence all cats sit quietly is true, then we know from that all black cats sit quietly is true. We also know that the sentence all cats sit is true. This concept, where some sentences are true because other sentences are true, is called entailment. We can remove the first set from the sentence and we get all x sit quietly. This is our function that we can apply to a set to fill in x. If every member of the set sits quietly, the value is 1. Otherwise, the value is 0. If all cats sit quietly is true, it means f of cats is 1. Since we then know all black cats sit quietly, f of black cats is 1, and cats is a superset of black cats, we can treat this as a monotonically decreasing function. But that's just for the first argument of all. For the second argument, the set of things that sit quietly is a subset of the set of things that sit. This is also monotonic, but in the other direction. So all creates contexts that are downwardly monotonic for the first argument, but upwardly monotonic for the second argument. Every is the same. Every cat sits quietly entails every black cat sits. Other quantifiers have other patterns. Some and many are upwardly monotonic for both arguments. Some cat sits quietly does not entail some black cat sits, but it does entail some animal sits. Fewer than 3 and no are downward for both arguments. So these analyses involving monotonic functions have been examples of how abstract mathematical properties can manifest in language. I hope you learned something, and thanks for watching.